Hi, hello everyone. My name is Jialin. I'm from the Computer Networks group in the computer science. Today I will talk about the telesurgery and the corresponding networking challenges. Here's the outline. First, I will introduce what is telesurgery, what's the current progress, and I will give some example telesurgery setup, the reasons why we need telesurgery, and some related areas. Because the real-time and distance and the locational requirement make a network, make a computer network the biggest barrier of telesurgery. So in this presentation, I will focus on the networking challenges and the requirements. Based on the networking challenges and the requirements identified, we will talk about the networking options for telesurgery. Finally, I will give some conclusions and insights. The telesurgery is also called remote surgery. It's a sub-area of telemedicine. It's referred to the operations over long distance using surgical robots. It fits to the situation where specialists is unavailable locally. There are some key characteristics. First one is the human surgeon serves as the master who controls the robotic surgeons. The robotic surgeons serve as a slave, taking the command from the human surgeon and operate on the patient. The second character of the telesurgery is the human surgeon and the patient and the robot are separated by long distance. Also, the computer network is the key component to break the distance barriers for the telesurgery. The voice over IP and the video guidance and the control traffic are all sent through computer networks. There's some reasons why we need telesurgeries. The biggest reason may be in the situation where the surgeons or specialists may not be available locally. In such a situation, the telesurgery can provide medical care to patients otherwise get untreated. Some examples may be some new state-of-the-art procedures may not even be available in some major cities. The patients may also not be survivable to long journeys. Also, because the quality of surgical proficiency is not geographically consistent, and it's regularly considered that the quality of surgery in the remote area or rural area is poorer than the biggest cities. There may be also some possibilities in the future to provide medical aid to the developing countries. Also, the telesurgery makes it possible to deliver medical care to injured soldiers in the war zone. And there's also potential to provide medical care to the space station and the aerospace travel. Also, the telesurgery can enable the collaboration of surgeons in various locations. As we know that some complicated surgery may require the surgeons from different departments, which may be difficult to collect them together at the same place and at the same time. It also enables the expert to proliferate their scale. It can also satisfy the educational purposes, because you can use telesurgery to train the surgeons and monitor some operations. The telesurgery can also reduce the cost on patient and the surgeon travel. This is the most obvious one. The first telesurgery performed on human is in September 7th of 2001. It's called the Operation Lindbergh. The surgery was performed between the United States and France. After that, the telesurgery was performed in many countries. Normally, the distance for telesurgery is about hundreds of or thousands of kilometers. We know that at the beginning, the cost of devices is quite expensive. A set of such devices may cost over $1 million. So therefore, at the current stage, the telesurgery is mostly proof of concept and for educational purpose because of the cost, technical, and complexity reasons. Here's the example telesurgery setup taken from the Operation Lindenberg. The surgeon was located in New York City, and the patient was in France. They're connected using fiber cable with a bandwidth of 10 megabits per second. The surgeon operated on the robotic command station, and the signal was digitized and transferred by the network to control the robot. And also the situation of the patient was taken by cameras, and after they coded by the image processor, the signal was sent back to a monitor before the surgeon. The Operation Lindenberg provided two major contributions. First, it's a proof of concept. It proved that the telesurgery is applicable. The second contribution of the operation is that it provides some guideline for us for the further researchers. For example, from the Operation Lindenberg, it says that the command channel they used to control the robot and get the feedback from the robot back to the surgeon, the traffic is about 60 kbps per second. And actually the video traffic takes over 70% of the overall traffic, which is 700 kilobytes per second. And we also know that for the fiber optics, the transatlantic delay for the round trip time is about 88 milliseconds. And we know that another delay is contributed by the image processor. In order for the surgeon to get the high quality images, it takes about 70 milliseconds to compress the image, then send over the network link. Telesurgery may benefit and require the research and technologies from many areas. For example, in the health-related areas, we need the medical science research and education, and the management and the administration. Then in the computer science area, we need the computer network, image processing, human-computer interaction, and artificial intelligence, and so on. Then in the electrical and mechanical engineering, we need the control theory, robotics, and the digital imaging, and so on. Because the network may be one of the biggest barriers for telesurgery, in the following presentation, I will focus on the networking challenges and the requirements, and also for the networking options. So there's some data taken from the Operation Lindenberg. We know that for the control traffic, each packet is about 80 to 160 bytes per packet. And we also know that the bandwidth is about 700 kbps per second for video and 6 kbps per second for command channel. We know that for the network delay, the comfort zone is less than 330 milliseconds, and the surgeon claim that they can adaptable up to 500 milliseconds. So network is one of the biggest barrier. We know that it requires some reliability and availability. So the network link may not always available. The bandwidth also may not be always promising. Also, we have problem with the order packet delivery in the current internet architecture. Also, the network delay determines how fast the robotic can react to the surgeon's command and how fast the surgeon can confirm the robot's movement. We also will talk about the privacy and the security issues later. So the network physical media is the most important component of computer networks. We know there's a twisted pair copper and the cables. They provide mostly for the local access and the access from the end user to the internet service provider. For the fiber optics, it's mostly found in the backbone of the internet service provider. There's also the radio channel for the wireless local area network, which is very familiar with 802.11. And also there's some wireless WAN protocols. I want to mention that for the first three protocols, actually they cannot satisfy the bandwidth requirement. For the 4G is short for the fourth generation of wireless protocol. It can provide bandwidth up to 100 megabytes per second, and it can provide the communication of distance of several hundred kilometers. Also, for the satellite radio channel, we know that because the geostationary satellites is about 36,000 kilometers above the Earth, it provides a delay of at most minimum of 500 milliseconds, which we cannot satisfy the requirement of telesurgery. So another opportunity is to use the low altitude satellite, which can provide the delay of between 100 milliseconds to 200 milliseconds. So in summary, here's the applicable options. So as the future techniques, we may want to use the low altitude satellite and the 4G to provide access. Here's also a network link requirement. With the physical media, it's not enough because we know that the current internet is a best effort. It's based on packet switched. And there's no routing path specification available at the user level. For example, if you want to send a packet from my home in Waterloo to the University of Waterloo, the packet may actually travel to Chicago first, then come back to the university. So in that way, because you cannot define the path for the packet to travel, you cannot determine the delay on each packet. Then it may result in the problem that some packet may get a larger delay, some packet may get out of order. Also, for the current internet architecture, there's no resource reservation available. Therefore, there's no delay order and bandwidth guarantee available for the application of telesurgery. So we know that the desirable network and the link layer protocol need to provide the functions for path selection and also for the bandwidth and the resource reservation. There's some currently available protocols. The first one is the ATM, stand for asynchronous transfer mode. It is also packet switch based. It actually provides a virtual circuit, which on each packet it put a label so that you can, during the connection setup period, you can define the path for the packet to travel. In this way that you can make every packet travel along the exact same path. Therefore, you can make the resource reservation to make a constant rate service. And also, there's some other opportunities to use MPLS and resource reservation protocols. So here's the some possible solution we think about. It's we may use the 4G and the fiber optic and the satellite to provide the required delay for the telesurgery. So we know that the beta rate and pocket loss is unavoidable. Mostly we can use the checksum facility provided by hardware and the software. Basically, we treat the packet with errors as loss and the packet loss as out of orders.
Go to your last slide.
Yeah. Here's the conclusions. We know that the telesurgery seems to be promising, and there's most of the technique is still in the experimental stage due to the cost and complexity considerations. There's still limitations tied with computer science problems. In particular, networks may be one of the biggest barriers, and there's some networking solutions exist currently and in the future, although they may be expensive. Here's some reference, and thanks. Question, please.
Is it a feasible solution for them to develop new transfer protocols? You said that the ones that are currently there don't quite cut it. Why haven't they gone on to do these new protocols?
Because the big problem is that in the current internet point-to-point access protocol is in the dominant position, so that it's not so, because everybody is every traffic is rely on right. It's not quite feasible to replace them with new protocol. That's the big problem. So maybe in the future, step by step, these new techniques may be propagated to the internet structure, then definitely telesurgery can benefit from those protocols and the new techniques.
One or two, I think you said megabytes a number of times when you should have been saying megabits. I'm not positive.
Oh, yes, megabits per second.
It should be mostly megabits. It was 100 megabits, not 100 megabytes. It's almost a factor, well, it's factor of 8 difference. So the thing that surprised me is that the work I've read about in this from the proceedings of the IEEE indicated that for surgical, for fine surgical activities, the maximum delay was 45 milliseconds, not 500 milliseconds. That's a factor of 10 difference. 45 milliseconds. So I was quite surprised at the size of these tolerable delays. It might be something you should check out. I read this article relatively recently in the last year, and that in fact it practically limited distances by any means, including fiber optic, to a few thousand kilometers because of the speed of light in the fiber. But that's just something to check out. One of the areas that I wanted to ask you about, you had computer science and other areas there, but this topic relates to the human factors. In other words, it is a human surgeon at one end, and
yes, right.
organs and blood at the other end. And one very big area of importance is the ability of human beings to not overcorrect for an action when the feedback is delayed, and that is a problem. It might be something that you want to look at and add to your list there. But any comments on that, the human factors there?
Yes, right. Actually, it's related with the network delay, because if the network delay is too huge, you may either overshoot or you undershoot. That is definitely undesirable.
That's right, and that's the wrinkle, is that my reading says that the acceptable delay is 1/10 of what you say it is. So both of us need to go back and get that.
Yeah, actually, I get this 330, the number from the paper for the first telesurgery on human. actually they deduct a series of experiments to make the artificial delay on the link. So the delay is from tenths of millisecond to maybe to 1,000 millisecond. So then the surgeon report if it's still they can adapt to this kind of delay. So finally, the surgeons argue that for the delay below 330, they can be adapted to that with no any difficult. But when the delay is above 330, but below 500, they can adapt to that. Under that, they cannot do the surgery safely.
The issue here may be that may be a very early paper, the 2001 thing, so that currently I think a much more stringent guideline is given for delays, but that needs to be checked.
Yeah.
Another really dumb question is, why did they call it the Lindbergh project? Why?
Because maybe this is the first step for the telesurgery on human. It's important.
So what was the relationship to the name Lindbergh?
Because the Lindbergh is actually the first craft to provide the carrier from Berlin to New York City. It's the first one. So there's the first step on the telesurgery.
Charles Lindbergh flew across the other way, actually, but he was the guy who first crossed the ocean in a plane.
Yeah.
Across the ocean. So I just wanted to know if you knew that or not.
Yeah.
Any other final questions or comments? Thank you very much.
Okay, thank you.